So far we have used the LMTD method for heat exchanger calculations and heat exchanger designs, but LMTD would require the knowledge of all the 4 temperatures. If the inlet temperatures are only known and the outlet temperatures are not known, use of LMTD would require an iterative procedure. So, in order to avoid the iterative procedure, a separate method, a different method that does not require the knowledge of the outlet temperatures as well is proposed and is being used, which is known as the effectiveness NTU method. So, we have to first define what is effectiveness and what is NTU. NTU stands for number of transfer units. So, what this number of transfer units mean, we first have to define. So, when you think of the effectiveness first, let us try to visualize a system in which a hot fluid is entering and its temperature is changing from THI, which is the temperature of the hot fluid on the at the inlet, and THO, where it is the temperature of the hot fluid at the outlet. So, when you think of the overall heat balance, the Q which the hot fluid has lost and which has been transferred to the cold fluid, the hot fluid, the loss of energy of the hot fluid can simply be expressed as m dot H Cph multiplied by Th inlet minus Th outlet. Similarly, the same amount of heat, since it is being used up by the cold fluid, so the heat balance written on the cold fluid would be m dot C, the cold fluid mass flow rate, multiplied by Cpc and Tc outlet minus Tc inlet. So, that is a simple heat balance which expresses the rise in temperature of the cold fluid and drop in temperature of the hot fluid, and a simple mass balance, simple energy balance would give us that whatever be the heat lost by the cold fluid, gained by the cold fluid, is equal to the heat lost by the hot fluid. Now, when you think a little bit more, I will write those expressions, and when you think a little bit more, you would see that there is a maximum temperature drop which will be possible for two different cases, two different scenarios based on what is m dot C Cpc and m dot H Cph. The product of these two, m dot C Cpc and m dot H Cph, which are the capacities of the hot fluid to release heat and the cold fluid to absorb heat, they together would give us some idea of the maximum temperature drop or jump which is possible for a specific situation, and this can then be manipulated to obtain an idea of what is the effectiveness of heat transfer in a heat exchanger. So, let us start from the beginning, writing a simple heat balance between the hot fluid and the cold fluid. So, we start over here that the effectiveness or NTU method, where NTU simply stands for number of transfer units. So, this is to be used if only the inlet temperatures are known. Use of LMTD requires an iterative procedure and an alternative methodology which is known as the effectiveness NTU method is to be adopted. So, what we are going to find out is the maximum possible whenever we talk about effectiveness, we have to express it as a ratio, that is the denominator should be the maximum and the numerator should be the actual. any effectiveness is defined as the actual amount divided by the ideal or the maximum amount. So, in order to define effectiveness of a heat exchanger, we must find out what is the maximum possible heat transfer rate that is possible, that is maximum possible heat transfer rate of a heat exchanger. And this maximal possible heat transfer rate, let us call it as Q max, and see what is going to be the value or expression for the heat exchanger. So, if I provide the following thing, if I provide an infinite length of the heat exchanger, then the delta T should approach T H I minus T C I. So, the temperature of the hot fluid at the inlet and temperature of the cold fluid at the inlet in a heat exchanger, that is the maximum temperature drop that is possible. So, the hot fluid enters at T H I and leaves at T H O, whereas the cold fluid enters at T C I and leaves at T C O. So, the maximum difference in temperature which exists in a heat exchanger is the temperature of the hot fluid and the temperature of the cold fluid, both at the inlet. So, if we can provide an infinite length, then that is the heat transfer, that is what is going to be the maximum change in temperature which can be achieved by heat exchange between the cold fluid and the hot fluid. But what is going to happen? Which liquid is going to attain the maximum temperature drop first? Is it going to be the hot fluid whose temperature is going to decrease from THI to TCI, or is it going to be the cold fluid whose temperature is going to rise from TCI to THI? Obviously, which liquid is going to experience the maximum possible temperature drop provided an infinite length of the heat exchanger is provided would depend on the value of m dot C CPC and m dot H CPH. These capacities, which are the product of the mass flow rate and the specific heat, whichever capacity, the total amount of heat transfer remains the same, remains equal. The amount of heat lost by the hot fluid must be the equal to the amount of heat gained by the cold fluid. But which liquid would face the maximum possible temperature drop would strongly depend on the value of the m dot Cp. So, the m dot Cp, whichever is lower between the hot fluid and the cold fluid, the value of m dot Cp, if it is lower for, let us say, for the hot fluid, then the temperature drop, the maximum temperature drop would reach faster for the hot fluid in comparison to that of the cold fluid. So, since the value of Q, which is m dot Cp multiplied by delta T, is the same both for the hot fluid and for the cold fluid, whichsoever fluid has smaller value of m dot Cp, the delta T drop or rise would be faster for that fluid. So, if for example, if the m dot Cp for the hot fluid is lesser as compared to the m dot Cp of the cold fluid, it is the hot fluid which is going to experience higher drop of its temperature. So, the hot fluid in that case would reach the highest possible temperature drop in a heat exchanger, which is THI minus TCI. So, when the hot fluid has reached that temperature difference, your simple heat balance would tell you that the cold fluid is yet to reach that delta T, which would give us some idea of the heat transfer under that situation. So, let us write it and see what it gives rise to. So, for cold fluid temperature capacity, if it is less than the capacity of the hot fluid, and C is simply m Cp m dot Cp, if it is H, this is going to be H, for the C it is going to be C. So, if Cc is less than Ch, then Q max would be capacity of the cold fluid times Thi minus Tci. So, Thi minus Tci, as I have explained before, it is the maximum possible temperature drop in the system. So, if Cc is less than Ch, then this Q max would be this. If it is the other way around, so please note that in both cases the temperature drop remains the same. Whichever is whichever is smaller, it would reach the maximum temperature drop faster. Okay. So, the effectiveness, so I guess these two are clear to all of you, and then the effectiveness for anything which is denoted by epsilon in this case is the actual heat transferred by the maximum heat which is transferred. So, this is actual heat transferred by maximum possible heat transfer. So, epsilon is therefore C of H, the actual heat transfer, the drop of the hot fluid from the inlet to the outlet. So, this must be the heat which is transferred actually by the hot fluid, which should also be equal to C of C T C out minus T C I. So, it can be expressed either the actual heat transfer can either be expressed in terms of the hot fluid losing energy or the cold fluid gaining energy. The denominator in both cases would be the minimum of the CH and CC. Whichever is smaller is going to reach the maximum possible temperature difference faster. So, therefore, the maximum possible heat transfer must be equal to C minimum, that is the lesser of CH or CC multiplied by the maximum possible drop. So, the denominator remains the same for both cases, and you can express whichever you can express in whichever way you want, whichever is convenient, either in terms of the hot fluid or in terms of the cold fluid. So, I am going through this part once again so as to ensure that there is no confusion in your mind. A fluid which has a lesser capacity, its temperature drop is going to be more as compared to a fluid of higher capacity when the heat transferred between the two is identical. So, for a cold fluid with a lesser value of the capacity would have a higher temperature drop, and this higher temperature drop would ensure that it is going to reach the maximum possible temperature drop faster as compared to that of the hot fluid. So, the minimum of CH and CC, the capacity of the hot fluid and the capacity of the cold fluid, multiplied by the maximum possible temperature drop, which is THI minus TCI, would provide the maximum amount of heat transfer which is possible. So, the effectiveness, which is always defined by actual divided by maximum. So, the actual can be expressed based on either the cold fluid or the hot fluid, and the maximum would simply be equal to minimum C minimum of CH and CC multiplied by the allowable maximum allowable temperature jump, which is THI minus TCI. So, therefore, the effectiveness, that the way we have defined, must lie within a range of 0 to 1. Okay. So, that is what the effectiveness of a system should be. I mean, generally whatever efficiency effectiveness that we define would vary between 0 and 1. So, the effectiveness, the way we have defined, ensures that the effectiveness of a heat exchanger will be between 0 and 1. So, your epsilon should be within this value between 0 to 1, and it appears only when you provide maximum this maximum possible heat transfer is when L tends to infinity. That means you provide very large length for the two streams to come to thermal equilibrium, perfect thermal equilibrium at the exit. So, if epsilon THI and TCI are known, the actual heat transfer can be expressed as Q as epsilon C minimum THI minus TCI. So, that is the purpose of the whole exercise. If the inlet temperatures are known, this is based on process conditions and process conditions and the physical property, because your C is simply defined as m dot times Cp. So, this C minimum is the minimum of this, then you can find out, knowing the value of epsilon, what is the actual amount of heat transfer. Sometimes it is also expressed for any heat exchanger, epsilon is a function of number of transfer units, C minimum by C maximum. Okay. So, this NTU is defined as UA by C minimum, and NTU is nothing but number of transfer units. I will explain it slowly. We understand that if I know epsilon, I do not need to know what is the outlet temperature. Only a knowledge of the inlet temperature would be sufficient to find out the value of Q, provided I know epsilon. So, our effort from now on would be to find out how one can obtain the value of epsilon, be it analytically or through the use of a series of graphs which are nothing but a solution of this, nothing but a representation of the analytical solutions which are available. While doing so, we also understand that this epsilon, the effectiveness, is a function of the ratio of C minimum by C maximum. So, if your C minimum, the capacity minimum is corresponds to that of the cold liquid, then this simply would be the C of the cold fluid divided by the C of the hot fluid. And another parameter, NTU, which is the number of transfer units, is added in here. That is an effect of the process the effect of the heat transfer coefficients, effect of the heat transfer area on this. So, which NTU is defined as U times A by C minimum, and the concept of number of transfer units would also appear subsequently, as you would see in your studies of heat transfer. So, number of transfer units would give you some sort of an idea of the overall performance of the system based on the some overall coefficient. In this case, it is heat transfer coefficients, the area involved in heat transfer, and the capacity factor, which is C minimum. So, if I know my epsilon as a function of NTU and C min by C max, then from this relation, knowing the value of epsilon, knowing the value of inlet and outlet temperatures of the inlet temperatures of the hot fluid and inlet temperatures of the cold fluid, I would be able to obtain what is the total amount of heat transfer in the heat exchanger. So, the entire emphasis from now on would be to find out this relation, and I would show you just one example of how this epsilon can be calculated for parallel flow heat exchangers. Similar examples, similar solutions are also possible, are also available for counterflow heat exchangers and various other flow configurations. So, if you know the flow configuration, if you know the other relevant parameters, then you should be able to obtain what is the value of epsilon, either from a series of relations which are provided or the graphical representation of those relations. So, it becomes quite easy as compared to the LMTD method from those references which are provided in any textbook to find out the total or overall heat transfer, the total amount of heat transfer, and then go for the further design of the heat exchangers. So, let us start with one simple case of evaluating epsilon for a specific flow configuration. The one which we are going to do is to find out the relations between effectiveness and NTU, and we are doing it for a parallel flow heat exchanger. With C minimum equals CH. That means the minimum of the capacity is due to for the hot fluid only. So, what is the definition of epsilon? It is the actual amount of heat which has been transferred. So, capacity of the hot fluid THI minus THO, which is the temperature drop of the hot fluid multiplied by the capacity, and the maximum amount of heat transfer possible, which is C minimum, the maximum amount of temperature drop or jump which is possible in this case. And since my C minimum is equal to CH in this case, that is what we have assumed. So, these two will simply cancel out, and therefore, the effectiveness can be written as THI minus THO as CH is equal to C minimum. This has been provided. So, this is parallel flow heat exchanger. So, a pictorial representation of this would simply be, this is THI, THO, this is TC out and TCI. So, this one is delta T, we call it as delta T1, this is delta T2, is the difference in between the temperature between these, sorry, this is parallel flow. this is not the one. For parallel flow, it should look something like this. Both are traveling in the same direction. So, this is THI, this is TCI, this is TCO, and this is THO. The one that I have now drawn is parallel flow. This is for counter flow, that is not the one, since we have assumed parallel flow only in this case. So, the difference between the inlet is delta T1 and this is delta T2. Okay. So, that is how it should look like. And what is C minimum by C maximum? C minimum times delta T minimum must be equal to C maximum times delta T, MCP delta T. So, it is MCP this by MCP cold fluid must be equal to TCO minus TCI divided by THI minus THO. So, if you see here, m dot Cph multiplied by delta T on the hot side must be, for heat balance, must be equal to m dot C based on the cold side multiplied by the temperature drop in the cold side. So, from a simple heat balance, it would give you that C minimum by C max is simply the temperature, simply expressed as the ratio of the temperature difference of the two cases. So, if I think of Q from here, the heat that is transferred CH THI minus THO, which is CC of the cold fluid TCO minus TCI, and when I think it in terms of log mean temperature difference UA for the case of parallel flow LMTD, which is THO minus TCO, that is delta T2 minus delta T1, which is, so this is nothing but delta T2, this is delta T1, and the denominator would be ln of delta T2 by delta T1. So, this is the basic fundamental relation which connects the heat transfer is equal to the heat loss by the hot fluid, heat gained by the cold fluid, and in terms of transfer between the heat, if I include a heat transfer coefficient, a heat transfer area, then heat transfer coefficient times heat transfer area times the temperature difference, which is nothing but where the temperature difference, as we have seen before, is expressed in terms of a log mean temperature difference and not the average arithmetic average temperature difference. So, the temperature difference of choice to be used for this case is the log mean temperature difference, which is this. So, as you can see, this delta T1 keeps on varying in a non-linear fashion till it reaches delta T2. So, log mean temperature difference is the appropriate one. So, this is from heat balance, this is also from heat balance, where we are talking about the transfer of heat between the hot and the cold fluid. So, this, when I write CH, when we take it a bit further, then Q would simply be equal to minus UA by ln delta T2 by delta T1 is equal to multiplied by Q by Ch plus Q by Cc. How did you get into this? How did we get this one? So, we know that this is Q. So, Thi minus Tho Thi minus Tho is Q by Ch, and Tco from here, Tco minus Tci is Q by Cc. So, this is what we have in here. So, when you have Tho minus Thi, Tho minus Thi in here, Tho minus Thi must be equal to minus of Q by Ch. So, taking this one and this one, I can write them the difference as Q by Ch, with a minus sign, and taking into the consideration that Tci minus Tco, is minus Q by Cc, which is minus Q by Cc, the negative sign taken outside. This is what we have done. So, the log mean temperature difference definition Thi minus Tco and Thi minus Tci for the case of a parallel flow can also be written as Tho minus Thi, which is minus of Q by Ch, and Tci minus Tco can be written as minus Q by Cc. So, this is what one can obtain for the case of the heat transfer between these. See, the main purpose of this is to get rid of the outlet temperatures. So, wherever Tco or Tho appears, through the use of the heat balance, we try to get rid of this the outlet temperatures and see what we can obtain as an expression involving epsilon and NTU to express the heat transfer for such situations. So, I am not doing anything new, not bringing any new concept except the maximum possible temperature difference, and which of the fluid is going to reach that maximum faster as compared to the other. Whatever else I am doing is simply an algebraic manipulation of the expression in order to bring in order to get rid of Tco and Tho and express everything in terms of Cc, Ch, epsilon, U, A and Q. That is all I am doing. So, that is the only thing which we are doing in this specific exercise. So, when you come back to this once again, then ln delta T2 by delta T1 can be written, ln delta T2 by delta T1 therefore can be written as minus UA 1 by Ch plus 1 by Cc. So, if you look at this one, I will bring this over to this side. So, this becomes ln delta T2 by delta T1, and since Q is, so when I bring it to this side, the Q will cancel from all sides and I have minus UA 1 by Ch plus 1 by Cc. For the parallel flow, when I express it in terms of the differences, I understand my Ch is equal to the C minimum as we have defined here, and Cc is the C maximum. So, when I take Ch outside, it is simply going to be 1 plus C minimum by C maximum. So, Ch is assumed as the minimum and this obviously is therefore the maximum. So, this is the expression that you would obtain, and now I bring this NTU, which is defined as the one which is on the outside of this bracket. This is the expression. So, therefore, what I would get is Tho minus Tco by Thi minus Tci, which is this one. Since it is in the logarithmic form, it is simply going to be equal to exponential minus NTU into 1 plus C minimum by C maximum. So, what then I have is a relation which brings in the new concept NTU, which is UA by C minimum, and slowly I am transforming everything in terms of NTU, either NTU and epsilon, C minimum and C maximum. So, when you see the last expression that I have written, it still contains some of the outlet temperatures TCO and THO. So, if I can now get rid of these TCO and THO, then everything is going to be either in terms of THI, TCI, epsilon, C minimum by C max and U. That is our objective, that is what we would like to do. So, I will continue this in my next class and derive a compact expression for epsilon in parallel flow, where only the inlet temperatures are known, the outlet temperatures are not known to me. So, once we do that, we can have other relations for other flow geometries, for multipass systems, for cross flows and so on, for which in your text you would see the results are presented in a graphical form, and it becomes very easy, trust me on this, it becomes very easy to solve for the unknown temperatures in such cases and then proceed towards the design of heat exchange equipments. So, I will stop here today and I will pick it up from this point in the next class to complete our discussion on effectiveness NTU method.